Yeah, I will talk about path planning, at the same time maximizing information along the path that we are planning, we are trying to construct. So this problem comes from bearings-only localization of some target, let's say, that you want to measure the position as accurately as possible. But there are errors, and the idea here is to keep taking measurements so as to build some information and use that information to decrease the uncertainty in the estimation of the position, the locality of the given target. I will pose this problem as an optimal control problem. It's not completely new that some people posed it as an optimal control problem, but the job that's been done so far doesn't seem to be really taking into account all the possible ingredients an optimal control model could have. I will then give the numerical solution of the unconstrained case, which has been dealt with in the literature previously. Then we'll present some numerical solutions of a constrained case that I'm going to be constructing in this talk. So here is a picture of what I've described. So there's a point here, there's a target here which might be emitting signals. You may think of a search and rescue operation. That there's an observer. This observer can be a ship on the sea, or a vehicle on land, or a drone in the air. So this is a two-dimensional problem. So in 2 dimensions, observer has sensors on it, has a sensor on it. And this observer is moving at a constant speed v. So the idea here is to determine how this observer should move, because the motion of the observer does affect, you're building up information, how it should move so as to decrease the uncertainty about the estimation of the position of the target. So the only thing that is measured here is the bearing angle, but of course there is noise in that measurement, and that's what's causing the problems. One can write a very simple dynamics for the observer. Of course, in an ideal world, this observer will have a rigid body, and you would write all the rigid body dynamics. But in this case, we can just write the kinematic relationship. So we have this velocity v. The horizontal component gives you one equation in the x direction, and the vertical component will give you the equation in the y direction. So it's very simple. It starts at an initial point, and we define relative observer position in order to write down the overall kinematic equations neatly. So we have one differential equation for the x coordinate, and another differential equation in the y coordinate, and we are working with these differences. So measurement, as I said, it has noise in it, and that noise is assumed to be a zero mean sigma standard deviation normal distribution it's coming from. So what is done for this? There are many there are different measures, of course. That one of the measures that is used is the determinant of what's called the Fisher information matrix. Fisher information matrix can be obtained as the Fisher information matrix can be obtained as the inverse of the covariance of the maximum likelihood estimator error, subject to the point mass dynamics that we have. So you can see that we have in each element of this matrix, we have an integral. And the integrand involves the geometry of the problem. So one measure of information is the determinant of the Fisher information matrix. What is it related with? It's related with the ellipsoidal area of uncertainty or confidence area. With what confidence can you tell that your estimation is good? So typical approach is, okay, the covariance determines that area, and the Fisher information is the inverse of that covariance. So when you maximize the determinant of the Fisher information matrix, you are minimizing that area, that ellipse of that ellipse, the area of the ellipse of uncertainty. So the typical approach is to maximize the determinant of this matrix subject to the point mass dynamics that I've just described. Well, what are the existing approaches? Well, people started to work on this back in the 1980s, and there were the efforts continued in the 1990s. The initial works just involved, okay, proposing the model just that I've just proposed and discretizing it, Euler discretization, but that's a fair thing to do. And use descent methods for finding a solution. In 98, Passerius van Kappel, they show that they solved the Euler discretization of the Euler-Lagrange optimality conditions for the unconstrained case. Of course, there are no constraints on the control or the states. Well, you may ask what the control could be in this case. Well, if we want to maximize the determinant of the Fisher information subject to the dynamics that we have here, your control would be theta, the angle theta. And your state variables would be x and y. Okay, fair enough. These integrals are replaced by their Riemann sums, which corresponds to Euler discretization in another way of writing them. And then you Euler discretize the differential equations and use descent methods. But the difference between this Passerius van Kappel and the previous ones, Hamel et al. And Oshman Davidson, is that Passerius van Kappel really, by discretizing the equations coming out of the Euler-Lagrange equations, they somehow check the optimality conditions. But in the first efforts, there is no such thing done. And then you look at the literature and you ask people who work in this area, okay, well, the optimality conditions, are they checked in a more general setting? The answer is no, because you see that people put some constraints on things because reality dictates that. There are restrictions in the motion variables. But then the typical approach is the approach that was assumed in the 80s and 90s, and discretize and find a solution. And Also, you note that there doesn't seem to exist a model, a properly posed model with a specified initial course. Initial course is, again, just to remind ourselves, is the heading angle of the vehicle, which appears in the dynamics here. And also in these models, there doesn't seem to be constraints on the rate of theta, which is very important because it tells you the vehicle at what speed, at what rate the vehicle is going to be maneuvering. It's very important because it's to do with the curvature. It determines the curvature of the path that the vehicle has to follow, and you don't want sharp turns because a physical system may not negotiate those sharp turns. So owing to these deficiencies, let's say, in these modeling efforts, I would like to go ahead with writing down an optimal control model for this very widely studied example. We define here new variables. These are the entries of the Fisher information matrix, but integrated up to time t. So Z1 is given as the integral from 0 to t. Z2 is given as this element, and Z3 is given as the off-diagonal element. The off-diagonal elements are the same. It's a symmetric matrix. Anyway, this is useful. Why? Because then we can write down the determinant of the Fisher information matrix in a neat form as follows. Subject to these equations, but from these equations we can differentiate both sides to get differential equations and add them to a model. So this gives us an optimal control model, which looks more or less a bit more in standard form. I mean, when you say an optimal control model, you have some objective functional to minimize or maximize, and subject to ODEs. Of course, you may have PDEs in general or algebraic equations as well, but in the classical models, you would have ODEs. So this is what's being solved without showing this model explicitly though. So here the state variables are, or the motion variables if you like, x, y, and Z1, Z2, Z3. The differential equations are written in these variables. And in an optimal control problem, you always have a free function to choose. And this function, because it's completely free, now completely free, I mean, you don't usually, it's not really common to fix an end, because then it might mean that you may have to change that endpoint or that value of the control abruptly, which is not allowed. It requires an impulsive change. So the control theta here, when you choose control as theta, then I mean, naturally you cannot really write down what initial course your vehicle has. However, it's interesting to add another equation, which is the rate of change of the heading angle, written in this way, where we can specify the initial angle of the vehicle. Because suppose that vehicle received a signal from the back, then this vehicle has to maneuver around to direct itself to the point where the signal is coming. So it is really, it looks to me very essential imposing this theta of 0 equals theta 0. But I couldn't really find any reference where this is specified. And I asked a couple of colleagues who work in this area. They also said that, well, they haven't seen it being specified. Maybe I'm missing something. When we write it in this way, theta is not a control anymore. It's a state variable. So now we have 6 states, and we have a control variable, which is u. But unfortunately, here we have no solution. Why? Because unless you choose theta 0 to be the optimal value of the previous problem, P1, then you will have to have an impulsive change in the control, a point change, jump. So therefore, no solution. However, it's again natural to constrain the rate at which the heading angle will change. And when we impose that here on u, I've written here this, I'm writing it in terms of the constant speed v, and a. Here a corresponds to the bound on the curvature of the optimal path that we have in the xy plane. In fact, when you choose v as it's interesting to make a note here. If you choose v to be the unit speed, and you replace the Fisher information here by TF, suppose that you want to minimize the TF, subject to this dynamics, given for x, y, theta, then the equations for z1, z2, z3 disappears, and you have the celebrated Markov-Dubin's problem. In Markov-Dubin's problem, okay, you want to go, okay, not quite. You need to specify the initial and terminal points, but it's a version of that. In this case, you specify only the initial velocity, but not the terminal one. But it's a special case of still Markov-Dubin's problem, which consists of concatenation. The arcs can be shown to be consisting of circular and straight line segments. Anyway, so we have a much more complicated problem here. In writing maximum principle, well, I promise not to go into details. We write down the Hamiltonian function. Still has to be written in this way. We simply write down the right-hand side of the differential equations. We append them by means of these multipliers, lambda x, lambda y, and so on, which are referred to as the adjoint variables. And adjoint variables are defined in this way. They are the negative of the partial derivative with respect to the variable the adjoint variable is associated with. We have the transversality conditions for each of these differential equations. Okay, and it's interesting to note here that, okay, let's try to work out just by inspection lambda theta dot. It's rather straightforward. So it's negative of h theta. So take the derivative of h with respect to theta, which involves only these terms. So we will have lambda xv sine theta with a minus sign, plus lambda yv cos theta with a minus sign in front of the whole term. But then at the end point, lambda x and lambda y, because of the transversality conditions, it tells us that they are 0 because the state variables are not specified at the terminal point. That's the reason why they are 0. So the derivative, not only lambda theta, but its derivative is also equal to 0 at the endpoint. Well, I'm emphasizing this because it's going to be important in checking the optimality conditions when we discuss later on the numerical solutions. Okay, this is, then we can write down the maximum principle. Given the definitions of these adjoint variables that we've written, if U is optimal control, and also the adjoint variable vector is never the 0 vector for any t in the time horizon 0 tf, Then U is a minimizer of the Hamiltonian function, which can be written simply as this, because this is the only term of the Hamiltonian function which involves the control. For this one, well, really, W here is bounded by minus VA and VA. So the minimizer of this is, okay, depends really on the sign of lambda theta. When lambda theta is negative, then choose W to be the maximum possible value, which is VA. When lambda theta is positive, then take W to be the minimum possible value given in the interval for W, which is negative VA. So we can encapsulate these in this expression. And there's a catch. When lambda theta is equal to 0, then we cannot say anything. So in other words, the maximum principle does not convey enough information for the optimality of U. When lambda theta is different from 0, because the takes either one upper bound or the other lower bound, we have a bang-bang type control. Because it's bang, bang, switching from, if there is a switching at all, it doesn't have to be, it switches between one upper bound to the other upper bound. From lower bound to the upper bound. If lambda theta is equal to 0 at isolated points, then the whole scheme will be bang-bang type, the whole optimal control. However, if it's equal to 0 in an interval, in a non-trivial interval, then the optimal control, the control is set to be singular. And how do you find? Sometimes you can recover this, what this singular control is, or you can write down the conditions which it has to satisfy. The first observation is that if lambda theta is equal to 0 in an interval, then all the derivatives of lambda theta is also going to be equal to 0 in the same interval, because it's a 0 function in that interval. All derivatives are going to be equal to 0. We define here the switching function. Sigma, it's a bit unfortunate, this notation, because I used it to mean standard deviation at the beginning, sigma squared, the variance. But here, because it's customary, it's traditional to use sigma as a switching, S standing for switching, to be the switching function, because that's what really lambda theta's role is. It determines whether control should switch from VA to minus VA, or indeed to singular when it's equal to 0 in an interval. In numerical experiments, I've used Ample IPOP suite. Ample, as many of you might already know, it's an optimization modeling language and software. And you can pair it up with one of the popular optimization, finite dimensional, nonlinear optimization software. And we use 2000 time grid points. So it gives a very large scale problem when you think that we have 6 differential equations. It immediately, and we have a control. So you have something like 14,000 variables, but the useful catch here is that the structure of the problem, again, we are coming to the notion of structure Claudia was emphasizing very much. The structure of the problem helps. Although I haven't done anything to do that, but the software do that. The structure is sparse. So the subproblems involve sparse matrices, and there are efficient sparse system, linear system solvers. So that really helps us obtain solutions in 10, 20, or 30 seconds or so, such large problems. Ample can be paired up with other popular optimization software like Nitro, Algencan, a Brazilian group behind it, and SNOpt. Okay, if we start with the example given by Osman Davidson in 1999, they consider a vehicle at 0,5 and the target is at 0,0. Then the trajectories that you have to follow look like this, which maximizes the Fisher information. In other words, these trajectories make sure that, suppose that you have a maximum likelihood estimator, some filter, like Kalman filter, some kind of Kalman filter, they're going to perform at their best, that their estimate will have the smallest possible error or uncertainty. They're of different lengths. They correspond to different times. So if you look at the angle, heading angle here shown, this heading angle ranges, they all start at 180. And they are given at different times. For example, if a time of roughly 10 to 15 or 12 seconds is given, then you see how abrupt the change in theta is here. This is insane. I mean, no physical system can achieve this change heading. No vehicle can change heading in split second in that manner. So that justifies imposing the constraint. Also, the optimal solution appears to be always starting at 180. What if the vehicle is pointing in the other way around, other direction? So in the next case, we look at the same positioning of the observer and the target, but we impose a constraint on the turning rate, 5 degrees per second, and the observer is pointing in the opposite direction, 0 degrees, and then we get this kind of angle profile. As you can see, the angle is changing much more mildly. Here we have the optimal paths given for different durations of times. Well, the meaning of these durations is that, okay, you have 50 seconds to collect information and tell me where the target is. Or you have 80 seconds or 100 seconds. So in each case, you expect to get a bigger information value. But the shorter your time is, the more demanding the job is. But it's essential then to maximize the information, and that's what we are doing there.
Yeah, Yalçın, sorry to interrupt. Yeah. It's kind of, yeah. your time is kind of up, so.
Okay, I will finish very quickly in 2 minutes. Is that okay?
Yeah, sure.
Thank you. Okay. So here we can check the optimality conditions by looking at the switching function. When the switching function is negative, then we get the full 5 degrees per second rate for theta. And when it's equal to 0, then we have the singular control. The scales are quite changing from one instance to the other. So that's why I'm just zooming in to show that the switching points here from bang to singular changes as well. But the interesting thing here is that when time is near 160 seconds here, we get bang, singular, bang arc. A very small bang arc, but it's interesting, the emergence of that. This all needs, of course, more scrutinization, but numerically at least, that's what we are getting, and the optimality conditions are satisfied. So I've already told the observations. One more thing to add is that there are multiple locally optimal solutions, which is beyond this talk. And what further can be done? Well, state constraints can be added, an alternative objective functional can be tried, for which perhaps it's possible to say more from a theoretical viewpoint. And one can consider more than one observer, and multi-objective optimal control, like comparing Markov-Dubins and information maximizing curves. Thank you.
Thank you very much, Yalçın. And unfortunately, because we're a little bit on a tight schedule today, because Han Kun has to leave right after his talk.
No problem.
Yeah.
Thank
so
you.
can we take? Could Yalçın take the questions in the chat or in Slack? So if you have some questions for Yalçın, please type in chat or move to Slack and do it in Slack. So sorry about this.
Thank you very much.